Preparing for a Kafka Engineer at Confluent interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Explain Kafka's core architecture and the role of brokers, topics, partitions, and replicas. Kafka is a distributed commit log built around partition topics. Brokers store partitions, while each partition has one leader handling writes and reads and followers replicating the log. Producers choose partitions, usually through keys or round-robin behavior, and consumers read records by offset. Replication provides fault tolerance, and partitions provide horizontal scale. I would also mention that ordering is guaranteed within a partition, not across an entire topic, which influences key design and application architecture. While answering, focus on Kafka's distributed log model, broker responsibilities, partition-based parallelism, replication, leader and follower roles, and how these components collectively provide scalability, durability, and consumer independence. Question 2. How would you choose the number of partitions for a new Kafka topic? I would size partitions from both throughput and parallelism requirements. For example, if producers need 200 megabytes per second and one partition safely handles 20, I need at least 10, then add headroom for growth and rebalancing. I would also ensure the consumer group has enough instances to use them. More partitions increase metadata and recovery overhead, and changing the count can affect partitioning behavior, so I validate assumptions with load tests before production. Make sure to cover expected throughput, consumer parallelism, ordering requirements, key distribution, broker capacity, future growth, operational overhead, and the fact that increasing partitions can change key to partition mappings. Question 3. What happens when a Kafka broker fails, and how does Kafka recover? When a broker fails, Kafka detects it through controller or quorum mechanisms and elects new leaders for affected partitions from eligible replicas. Producers and consumers refresh metadata and reconnect to those leaders. With replication factor 3, losing one broker can be transparent if another in-sync replica is available. I avoid unclean leader election when data loss is unacceptable. I also configure acknowledgements and minimum in-sync replicas together so durability requirements are enforced during partial outages. In your answer, talk about controller detection, leader election, in-sync replicas, unclean elections, client metadata refresh, replication factor, and how minimum in-sync replicas affects availability and data safety. Question 4. How do Kafka producers achieve reliability and high throughput? I balance reliability and throughput through producer configuration and measurement. I normally enable idempotence, use AX=all, configure retries and delivery timeouts, and select compression such as Z-standard. Batch size and linger allow more records per request, improving throughput, while buffer memory prevents unnecessary blocking. I would monitor request latency, error rates, batch size, and buffer exhaustion. The correct settings depend on business tolerance for latency and loss, not on maximizing a single benchmark. Be sure to mention acknowledgements, idempotence, retries, batching, linger, compression, buffering, delivery timeouts, in-flight requests, and the trade-off between latency, throughput, and durability. Question 5. How would you design a consumer group for scalable and reliable processing? A consumer group lets multiple instances divide partitions while preserving processing order within each assigned partition. I would keep consumer count aligned with partition count, tune max.poll.interval.ms for the processing workload, and commit offsets only after successful handling. For long work, I would decouple polling from processing or use pause and resume carefully. Cooperative rebalancing and static membership can reduce disruption. Shutdown should stop intake, finish safe work, commit offsets, and leave cleanly. Focus on partition ownership, one consumer per partition limit, offset commits, polling behavior, rebalancing, processing duration, static membership, cooperative assignment, and graceful shutdown procedures. Question 6. What is the difference between at most once, at least once, and exactly once processing? At most once commits before processing, minimizing duplicates but risking loss. At least once commits after successful processing, preventing loss but allowing retries and duplicates. Exactly once requires transactional coordination, so consumed offsets and produced records become one atomic result, as supported by Kafka Streams. I still treat external databases carefully because Kafka transactions do not automatically cover them. In practice, I often combine at least once delivery with idempotent writes, unique event identifiers, and deduplication. In your answer, distinguish loss from duplication, explain offset commit timing, discuss idempotent processing, transactions, Kafka Streams exactly once semantics, and clarify that external systems require separate coordination. Question 7. How would you investigate consumer lag in a production Kafka cluster? I first quantify lag by consumer group and partition, then compare current production rate, consumption rate, and historical baselines. A single hot partition suggests key skew, while broad lag may indicate slow processing, broker saturation, network issues, or a downstream dependency. I inspect rebalance frequency, poll violations, fetch metrics, error logs, and consumer CPU. Remediation could include scaling consumers, optimizing processing, increasing partitions, or fixing the bottleneck rather than simply adding instances. Make sure to cover measuring lag by partition, identifying whether production or consumption changed, checking rebalances and errors, examining throughput and processing latency, and validating broker, network, and downstream dependencies. Question 8. What causes consumer rebalances, and how would you reduce their impact? Rebalances occur when group membership or partition assignments change, or when a consumer misses heartbeats or exceeds its polling interval. They can pause processing and create duplicate work if offsets were not committed. I reduce impact by separating polling from long processing, tuning session and poll settings, using cooperative sticky assignment, and enabling static membership where appropriate. During deployments, graceful shutdown and staggered replacement prevent unnecessary group churn. I verify improvements through rebalance and processing latency metrics. Discuss membership changes, missed heartbeats, poll interval violations, session timeouts, assignment protocols, static membership, cooperative rebalancing, graceful deployments, and how rebalances affect latency and duplicate processing. Question 9. How do Kafka partition keys affect ordering, scalability, and data quality? A partition key determines where related records land, so it should reflect the entity whose order matters, such as account ID or order ID. Kafka preserves that key's sequence within its partition, enabling reliable stateful processing. Poor choices can create hot partitions or scatter-related events. I test distribution with realistic data, define behavior for null keys, and document whether key changes are backward compatible. Key design is therefore both a performance and correctness decision. While answering, focus on deterministic hashing, per-key ordering, hotkeys, null key behavior, partition balance, business aggregation requirements, and the consequences of changing key strategy after data is already flowing. Question 10. What is log compaction, and when would you use it? Log compaction retains the latest value for each key rather than every historical record, making a topic useful as a durable changelog or current state cache. A null-valued tombstone marks a key for deletion after cleanup processing. Compaction is asynchronous, so old records may remain temporarily. I would use it for customer profiles, configuration, or Kafka Streams state restoration, but not for audit events where complete history matters. I also monitor cleaner activity and segment configuration. Be sure to mention key-based retention, tombstones, latest value semantics, cleanup timing, compaction versus deletion, consumer reconstruction, and why compaction is unsuitable when every historical event must remain available. Question 11. How do Kafka retention policies work, and how would you select them? Kafka retains segments according to time, size, or both, and deletion usually occurs after segments roll rather than immediately at the exact threshold. I choose retention from replay, recovery, compliance, and cost requirements. For example, a payment event stream may need 7 days locally, while an analytical topic might use longer retention or tiered storage. I estimate daily volume, replication overhead, and growth, then validate disk headroom and recovery performance before setting production limits. In your answer, cover time-based and size-based retention, segment behavior, storage forecasting, replay requirements, compliance, deletion timing, tiered storage, and the relationship between retention and consumer recovery windows. Question 12. How would you evolve Kafka event schemas without breaking consumers? I use a schema registry and enforce compatibility checks in C and deployment pipelines. Additive fields with sensible defaults are usually safe, while renaming, changing types, or removing required fields can break consumers. I select backward, forward, or full compatibility based on rollout direction and operational needs. Producers and consumers should be upgraded in a controlled sequence, with representative fixtures and contract tests. Schema governance turns an informal event payload into a dependable interface between teams. Focus on schema registries, compatibility modes, backward and forward compatibility, additive changes, defaults, field removal, subject naming, serialization formats, and producer-consumer rollout sequencing. Question 13. What is the role of Kafka Connect, and how would you troubleshoot a failing connector? Kafka Connect standardizes movement between Kafka and external systems through source and sink connectors, with workers distributing tasks. I troubleshoot by checking connector and task states, worker logs, consumer lag, converter configuration, authentication, schema errors, and target system throttling. I determine whether the failure is transient or caused by a bad record. Retry and dead letter settings can isolate poison messages, but I verify delivery semantics and offsets before restarting or altering task assignments. Make sure to cover source and sink connectors, workers, tasks, offsets, converters, dead letter queues, retry policies, external system limits, connector status, logs, and safe restart or offset management decisions. Question 14. How would you compare Kafka Streams with a custom consumer application? Kafka Streams is my preference for Kafka native transformations, aggregations, joins, windows, and stateful workflows because it manages partitions, local state stores, changelogs, and recovery. A custom consumer is better when processing involves unusual orchestration, complex external transactions, or framework constraints. Streams can create repartition topics and require careful topology design, while custom code requires me to build more operational safeguards. I choose based on statefulness, integration boundaries, latency, and the team's ability to operate each model. In your answer, discuss stateful processing, joins, windows, repartition topics, state stores, exactly once support, operational control, library abstractions, and when a custom consumer provides better flexibility. Question 15. How do Kafka transactions support exactly once stream processing? Kafka transactions atomically publish output records and commit the consumed offsets, so a restarted application does not expose partial results to redecommitted consumers. I use stable transactional IDs, enable idempotence, and configure transaction timeouts below broker limits. Producer fencing prevents an old instance from continuing after a replacement takes over. This protects Kafka to Kafka workflows, but an external database or API still needs idempotency or a coordinated pattern such as an outbox. Be sure to mention transactional IDs, atomic writes, offset commits, redecommitted isolation, producer fencing, transaction timeouts, aborted records, and limitations when external side effects are involved. Question 16. What Kafka security controls would you implement in a Confluent environment? I would secure transport with TLS, authenticate clients through an approved SASL mechanism, and authorize actions using least privilege ACLs. Producers should write only to required topics, consumers should read assigned topics and groups, and connectors need narrowly scoped access to source or sink resources. Credentials belong in managed secrets, not configuration files. I would also protect schema registry, restrict network paths, rotate certificates, and audit access and failed authentication events. Focus on TLS encryption, SASL authentication, ACL authorization, identity and secret management, network isolation, auditability, least privilege, schema registry permissions, and separate controls for brokers, clients, and connectors. Question 17. How would you monitor Kafka health and define useful alerts? I monitor the system at broker, client, and business levels. Important signals include under-replicated or offline partitions, active controller or quorum health, request latency, failed requests, ISR changes, disk utilization, network throughput, JVM pauses, producer errors, and consumer lag. Alerts should indicate an actionable threshold and owner, not merely create noise. I also track end-to-end event latency and throughput because a healthy broker can still hide a broken downstream consumer or business pipeline. In your answer, cover broker, controller or quorum, replication, producer, consumer, disk, network, and JVM metrics, plus actionable alerts for under-replicated partitions, lag, failed requests, and storage pressure. Question 18. A topic has uneven partition traffic and one consumer is overloaded. How would you diagnose and fix it? I would compare bytes, records, and processing time per partition, then inspect key frequency and producer partitioning. A hot customer or tenant may dominate one partition even when total traffic looks reasonable. I would confirm the consumer assignment and rule out downstream or message size effects. If ordering permits, I might use a composite or salted key and redesign aggregation. Otherwise, I would isolate hot tenants or add capacity elsewhere. Increasing partitions alone will not redistribute existing keyed traffic. While answering, identify key skew, hot entities, producer partitioning, message size, partition count, consumer assignment, and whether ordering constraints permit key redesign or workload decomposition. Question 19. How would you design a Kafka-based system to handle duplicate events and retries safely? I assume duplicates can occur, especially with at least once delivery and failures between processing and committing offsets. Each event should carry a stable identifier, and consumers should make side effects idempotent through upserts, unique constraints, or a deduplication store. Kafka producer idempotence prevents certain producer duplicates, while transactions help Kafka to Kafka flows. I separate transient retries from poison messages, use dead letter topics selectively, and monitor duplicate rates so replay behavior remains visible and controlled. Make sure to cover stable event IDs, idempotent producers, deterministic processing, transactional boundaries, deduplication state, database constraints, retry topics, dead letter handling, and observability for replayed events. Question 20. Describe how you would migrate a legacy messaging pipeline to Confluent Kafka with minimal risk. I would begin by inventorying producers, consumers, schemas, ordering guarantees, volumes, and failure behavior. Then I would define Kafka event contracts, provision secured topics, load test capacity, and run a parallel path with record counts, checksums, and business result comparisons. Consumers can migrate gradually behind feature flags, with offsets and rollback procedures documented. I would avoid uncontrolled dual side effects by making downstream writes idempotent. After stabilization, I would retire the legacy route and preserve replay capability. In your answer, discuss discovery, event contracts, dual publishing, validation, replay strategy, consumer cutover, rollback, security, capacity testing, observability, and how to avoid inconsistent outcomes during coexistence. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.